In this video, we're going to look at solving inequalities again. Mostly here we're going to look at rational functions, but also some with absolute value and radicals. We're going to use the sign chart method again. If you prefer to work algebraically, that is fine. You can continue to use that method. For the inequalities here, what we want to do is just kind of expand upon the process we use with the polynomial inequalities. So we want to find the real zeros and the undefined values of my function. So remember, for a rational function, that's going to be where my denominator values are 0. If I have a radical, it would be what would make my denominator a negative value. So you just have to think about your function and where it might be undefined. Once I have those values, I'm going to mark them on the number line. So remember, these are my critical values, so I would mark those critical values on the number line. And then we're going to test each region of the number line to create our sign chart again, just like we did before, and then convert that into interval notation, because we're going to put our answers in interval notation. So looking at the example we have here, we have x minus 3 over x squared minus 16. So we know from this my denominator can't be 0, so x squared minus 16 is 0 when x squared is 16, which happens when x is plus or minus 4. So plus and minus 4 are my undefined values, so I'm going to mark those on my number line. Remember, these are undefined values, so I'm gonna put the open circles on there just to help us remember we can never include those, even if it has an or equal to sign on it, because those values are undefined. When I have a single rational expression, remember, to find my 0, I can just look at my numerator and set that equal to 0. So x minus 3 equals 0 when x equals 3. So x equals 3 is a 0. So I'm going to put the closed circle on there to help me remember that I can include that anytime I want to include the zeros. Could have gotten all that from the graph. So if you just graph this rational function from the beginning, you could see that your asymptotes are at -4 and 4, and then you could find this 0 right here, which would have given you the 3. So then we're going to test the values. Again, you can do that by hand. You can use if you've already graphed it, you can use your second trace value option, or you can just use your calculator and plug in values. So testing values less than -4 would be this section here. I'm going to get negative numbers. In between -4 and 3, I'm going to get positive numbers. Between 3 and 4, I'm going to get negative numbers. And then after 4, I'm going to get positive numbers. Then again, I'm going to go back to my inequality. In this case, it said less than or equal to 0, so I want the negative regions and the zeros. So here, less than, remember, I can't include this -4 because that was an undefined value. And then between the 3 and the 4, I can include the 3, but not the 4 because that was an undefined value. So it's just a little bit of a extra thing that you have to think about with the undefined values here. So I'm going to give my answer here in interval notation. So -infinity to -4, parenthesis on that because that was an undefined value, and then from 3 to +4. All right, so here's a second example. A single rational expression less than or equal to 0. So I can work algebraically or from the graph here. So if I work algebraically to find my undefined values, I'm going to set that denominator equal to 0. I'm going to get x is plus or minus 3. So on my number line, I'm going to have -3, again, undefined. So I'm going to put the open circle there, and then +3, undefined. I need my 0, which again, since I have a single rational function, I can just set that numerator equal to 0 and solve it. So I'm going to get 2x squared is equal to 5, x squared is equal to 5/2. So x would be equal to plus or minus the square root of 5/2. We're just going to put that into decimal notation. We'll just use an approximate value there. This is approximately plus or minus 1.58. So I've got the -1.58, and then I've got the positive 1.58. Remember, these are zeros, so I'm going to put the closed circles on those. If you prefer, sometimes people just put like the z's and the u's above the number line to note the undefined values and the zeros. Then I'm going to do the sign chart. So my values less than -3 are going to give me positive. In between -3 and -1.58, negative. And then in between the -1.58 and the positive, positive 1.58, I get positive values. Between 1.58 and 3, I'm going to get negative values. And after 3, I'm going to get positive values. So I'm going to go back to my equation or inequality that I started with. This was less than or equal to 0, so I want the negative values and the zeros. So I want this section and this 0, then I want this section and this 0. So writing my answer in my interval notation, I'm going to go from -3 to -1.58. So parenthesis on the -3, square bracket on the -1.58, and then from +1.58 to +3, square bracket on the 1.58, and then parenthesis on the 3. If this had asked for exact values, so this would be -3 to negative radical 10 over 2, and then positive radical 10 over 2 to 3. All right, here's an additional example. This is not just a single rational function. This is actually two rational functions added together. So we have to be a little bit careful here. We can still get our undefined values from the denominators. So x plus 3 equals 0 is going to give me x equal -3, and x minus 1 equals 0 is going to give me x equal +1. So my undefined values are at -3 and 1. In order to find the 0, I would have to add these fractions together to combine them into one rational function, and then I could look at my numerator and set that equal to 0. So instead of doing that, I'm just going to grab that intersection from the graph here. So from the graph here, we can see that the intersection, which is my 0, is a -0.5. So on my number line, I'm going to mark the -3, which is an undefined value. I'm going to mark the -1/2, which is a 0, and I'm going to mark the +1, which is an undefined value. Then we can check our signs again. So less than -3 is negative values. Between -3 and -1/2 are positive values. Between -1/2 and 1 are negative values. And then after 1, we have positive values again. So I'm going to go back to my inequality, and it says greater than or equal to 0, so I want the positives. So I want this region including the -1/2, and then this region going to the right forever. So my answer is going to be -3 to -1/2, and then 1 to infinity. All right, taking a look at some examples that have some other types of parent functions in them. So this has an absolute value in it. It doesn't change the process at all. We're still just looking for what are my zeros and what are my undefined values. So when my denominator is 0, that's going to be undefined. So when x plus 3 equals 0, x equals -3, so that's my undefined value. My 0, remember, is going to come from where my numerator is equal to 0. So x minus 2 equals 0 gives me x equals 2. Again, we could get those from the graph. You can see the intersection of the axis at 2 here, and then you can see your asymptote is at -3. So I'm going to mark those values on my number line. So I've got a -3, remember that was undefined, and I've got a 2, which is a 0. Less than -3 are negative values. Between -2 or -3 and 2 again are negative values, and then after 2 is a positive value. So going back to my inequality, I have greater than or equal to 0, so I want the positive regions only, so to the right, and then I can include the 0, so I'll include the 2. So here my solution is 2 to infinity, and I'm going to do the square bracket on the 2 because we can include it because of the or equal to.